Good morning, welcome you to the next class on the inorganic chemistry of life, principles and perspectives. In the just previous class, we were looking at the electron transfer, general principles, phenomena, and when it comes to the proteins. And towards the end, we looked at the redox potentials. There are a lot of enzymes having different redox potentials because what is bound to the metal center is changing as well as the protein changes. These things change either if it is a heme protein or non-heme protein, and these ranges quite a lot, and this range is compatible with the range of the potentials that are found for various reactions that happen in the biological systems. And these I have shown through the couple of slides here, some reactions that takes place. These are all mostly the oxygen kind of reaction, all iron enzymes, so other kinds of reactions that occur. So these all span somewhere minus around 1 mole difference or so, which is reasonably well covered by all the enzymes. And you know how to understand this particular redox potentials, and I will explain you as this. So this should be understood from the delta G 0 is minus NF E naught, and if the E naught, that is redox potential, is minus, then it will be plus, that means reduction is not favorable. The E naught is plus, then the delta G is minus, and the reduction is favorable. So the more the positive reduction potential, the more that it will be in the reduced form. The more the negative potential is, the more its tendency to be in the oxidized form. Now you understand. So there are two forms for a redox thing. One is in the reduced form, other in the oxidized form. So relatively speaking, which one has a more positive, more in the reduced form, the other one will be in the more in the oxidized form. So if you understand this trick, the entire thing can be followed. So what is the trick? The del E naught potential, if it is more positive, that will tend to be more in the reduced. That means it will give away, it will take the electron. In the reduced form, it will be very happy, and if it is a positive negative potential, it tends to be in the more in the oxidized process. That means it will give away the electron. Okay. So the donor property or acceptor property of a center, a metal ion center in a protein depends upon its redox potential. So the more positive, it will be happy to be in the more reduced form. More negative in form, it will be more happy to be in the oxidized form. So that means an enzyme can go from a reduced form to oxidized form, back to reduced form and oxidized form. So in the process, it can change one electron transfer. And this, as I promised you in the previous class, we will be looking at some example. Let us look at it as an example of cytochrome C. We have already seen what is a cytochrome C earlier. I will also be showing again in the next. Maybe you can see back that one. So cytochrome C is the one which is shown over there. Here you can see that this is the one. It is connected through thioether linkages with the protein. Okay, and of course it has both the propionic acid groups, etc., etc. So this will be the part in the cytochrome C, and the remaining protein will be there, which I will show in a while. Okay, this is found in plants, this is found in animals, this is found in cellular, small unicellular systems, etc. It has about 100 to 120 amino acids with about 12 kilodalton. It's a small, relatively small protein. Interesting and important parameter of this is about 1/3 of its amino acids, if you look at across the various species, there is a sequence homology. So at least 1/3 of them is the sequence homology, and you should not forget that those residues which are close in the proximity of the heme, they are conserved in almost all the things, and reduction potentials are around plus 0.25, plus 3, etc. And these are involved in the electron transport chain in mitochondria. Okay. So these are involved in the electron transport chain. They are also involved in a variety of reactions like hydroxylation reaction, again involved through the electron transfer. It does not do the final hydroxylation, but it is involved in the process of allowing the electron transfer taking place. Aromatic oxidations, peroxidase activity, many of these kind of things. They are involved in apoptosis process, and they are involved antioxidative What is antioxidative? I mentioned earlier lectures that the O2 minus or other radicals, other species, ROS, reactive oxygen species. So, removing those reactive oxygen species is an antioxidative activity. So, antioxidative activity also. For example, O2 minus should be removed and the radical should be removed and make into O2. So, O2 is danger free and O2 minus dot is a highly dangerous or toxic. So, therefore, cytochrome C in its oxidized form, Fe3 plus means oxidized form, will take up this electron and go to Fe2 plus, cytochrome C Fe2 plus. That means the enzyme is reduced, the O2 minus is oxidized to O2. So, oxidized enzyme is reduced to reduced enzyme, and in the process of this returning, that will give this will iron 2 plus gets oxidized, that means it gives away an electron, and that electron will be given to this, and that will break down the peroxide into OH minus. Okay. So, the peroxide is is more toxic than OH minus. O2 minus dot is much more toxic. So, it converts into the less toxic forms of that too. But the role of this cytochrome is involved in the electron transfer basically in these kind of systems. Now, as you can see that there are different kinds of classes of cytochrome C's are there. Cytochrome C, if you see in the enzyme in the heme, there are the iron is connected with the 4 the pyrrole rings, the 4 nitrogens, and that is what is shown by this the tetragon of this. Then you have one more coordination 5th and one more coordination here 6th. Actually, this you can call it as 5th, this you can call it 6th. This is coming from the histidine, this is coming from the methionine. In some cases, both will be histidine. So, there are different kinds of cytochromes where you have both the histidines or histidine and methionine, and these are all influencing the ion center in terms of the ion spin state, is the ion center in terms of the ion spin state. So, if you have a low spin state, soluble cytochrome C, this is found in mitochondria, bacteria, high spin cytochrome C and a number of low spin cytochromes, they are found in the cytochrome C 556. What is 556? Is the absorption maximum wavelength 556 nanometer. 556 nanometer. So, now I explained you, I will not explain later on. Cytochrome C I have shown you, and the number that is coming next to that is the absorption wavelength. Then you have type 3 comprises of the low redox potential multi-heme cytochrome. Example, cytochrome C7, triheme, cytochrome C3, which is tetraheme. So, there are 3 hemes are involved, there are 4 hemes are involved, there is not 1, there is not 2, there are 3, there are 4. So, this is another kind of a thing. And the tetraheme proteins containing both histidine and histidine methionine coordinated hemes, and these come under the different class. So, class 1, class 2, class 3, class 4, there are so many kinds of cytochrome C's are involved. They are all cytochrome C family, it is called cytochrome C family. And just simple cytochrome C structure is shown over there, a lot of protein structure this side, protein structure this side, and here is a heme, and that is shown much more here. Okay. And you can see this heme is reasonably well exposed to the exterior. So, therefore, it can interact with the exterior, which can interact with another enzyme which can act as an acceptor, therefore, can give away the electron, get oxidized and reduced. All these kinds of things can happen here, both reduction and oxidation can happen. Okay, how the electron transfer occurs? As you can see that this example has been worked out by using ruthenium ammonia complexes. People have also studied with ruthenium pyridyl too. Let us take ruthenium ammonia complexes. They can be used, and you have the enzyme cytochrome C in the oxidized form will get into the slowly into the activated form, and this activated form in the presence of course this one, and it forms a complex, goes to the activated form, is ready for electron transfer, and the electron transfer going into this 1 will give the iron 2, C2 means iron 2. So, this goes through conformational changes of native cytochrome C to the activated complex. So, that activated complex will allow the electron transfer at a very fast rate. So, what is the slow means? It is the rate determining step. So, rate determining step here is the formation of the complex and the complex converted into the transition state or activated complex. So, conversion into the activated complex is the rate determining step. So, that means it is the reorganization energy that is the basically is favoring. So, once that is activated, then the electron transfer goes very fast. The Kd is around 55 second inverse. Okay. So, these are the kinds of things that we are looking at. So, these are capable of, depending upon the partner, this can act either as a donor or as an acceptor, because this all depends on the potential. So, all that I want to demonstrate to you is you have a ground state complex, and this complex has to be converted into an activated complex, therefore, energy is involved. And then of course, conductivity is the medium between the donor and acceptor. Now, let us say assume that the cytochrome C has gone from cytochrome C in the iron 3 oxidation state to a cytochrome C in the iron 2 oxidation state. How will it return back? That is explained over here, and this thing is done by the cytochrome C oxidase. There is an enzyme called cytochrome C oxidase, and this enzyme for biological inorganic chemists, this portion is important, or this portion either is one and the same, and this is the enzyme structure. So, this cytochrome C oxidase is a bit complex protein, having the 2 copper centers, having a heme A, having a heme A3, and having a copper B center. The whole thing is surrounded by the protein here, you can see that. Now, how does the electron transfer finally take place between the cytochrome C and cytochrome C oxidase? Let us assume cytochrome C is reduced form, it has to be oxidized, and that is what is done in this particular case. And let us look at to explain this. So, this is coming from the cytochrome C, and this is coming from the cytochrome C oxidase, and these two have a docking in this region. So, assume that the cytochrome C docks with the cytochrome C oxidase and forms a kind of a complex. You see that this region is the region where conductivity should work, and that is exactly the region of this. There are many details of this where the water is involved, etc. I will not go into details. This is coming from the cytochrome C, this part is coming from the cytochrome C oxidase. You see the 2 coppers, and there are some residues like the K3 and C14, cysteine and lysine, cysteine 14 number and the lysine 13. These two, which are coming from the cytochrome C, are extremely important. Similarly, the methionine 207 and tryptophan 105 coming from the cytochrome C oxidase are also equally important. So, this is the region. Now, if you take this center and to this center, and this distance is around 23 angstroms. But if you go through this particular path, this is called electron transfer path, and this is around 42 angstroms. Okay? And that is where, so these are important. How do we know these are important? You can mutate these residue, any of these residue or both these residues, similarly any of these residue or both of these residues, and the mutated protein will not do the electron transfer between the cytochrome C and cytochrome C oxidase. That means these residues are absolutely important. They are present in the corresponding enzyme, and that means this region is absolutely important. Therefore, the water present in this, the medium that is present in this is absolutely important. We will not go into details because that will come into purview of physical chemistry a lot, which I am not getting into the details of this. But as an inorganic chemistry, we need to know this center, we need to know this center, and what are the residues are involved. So, now you understand how an electron transfer is taking place between the cytochrome C and cytochrome C oxidase. In this case, between this region to the copper center, then it will go to the A3, then it will go to the A, etc., and then finally to the reaction center. So, we are not worried into that part of it, but so this is one example I have given you the heme containing. Let us look at one example for the non-heme containing. So, non-heme containing electron transfer proteins of iron are called iron-sulfur proteins. If you call iron-sulfur protein or non-heme, that is one and the same. And there are several classes, of which important ones I am going to explain in this course. There is 3 types. There are more types are there. So, one is there is just one iron and 4 cysteines are bonded, as you can see here, FeSCy cysteine 4 times. These are called rubridoxin, it is called rubridoxin. Then you have another case, one iron, 2 cysteines, another iron with 2 cysteines. The 2 ions are by 2 sulfido groups. This is called ferridoxin, but it is called 2 iron 2 sulfur ferridoxin. This is called rubridoxin or 1 iron sulfur protein, 2 iron 2 sulfur protein. There is another case which is 4 ions. So, each of the ion is connected to one cysteine. Where is cysteine is coming from? The cysteine is coming from the protein. It is not a cysteine, just simple amino acid, it is coming from the protein. So, the protein wraps around. So, like that it is shown over there, protein wraps around, and you can see the protein wraps around. So, all the 4 cysteines are coming from here, all the 4 cysteines are coming from here, all the 4 cysteines are coming from here. This is for 1 iron iron sulfur protein, this is 2 iron 2 sulfur protein, this is 4 iron 4 sulfur protein. So, this is called rubridoxin, this is called ferridoxin 2 iron 2 sulfur, this is ferridoxin 4 iron 4 sulfur. There are some more classes, but we do not need, just these are sufficient. There are proteins having different kinds of protein electron transfer, sometimes more than one of the same type, they are also there, but with some little modifications. So, therefore, their redox potentials will differ. Why nature has chosen so many? Because to control their redox potentials in various ways. Okay. So, I hope you understand 1 iron iron sulfur protein, 2 iron 2 sulfur protein, 4 iron 4 sulfur protein. Okay. So, in all these there are 2 types of sulfur linkages. One is from the cysteine sulfur, it would have been SH, which is called thiol, proton is lost, then this is called thiolato bridge, and this is called S2 minus sulfido. So, how do one differentiate these ones? Just take this protein, add some acid, mineral acid, and if you get hydrogen sulfide smell, that means you have a sulfide S2 minus, which is also known as inorganic sulfur, it is called organic sulfur. Cysteine sulfur is called organic sulfur, the bridge sulfur here is called the inorganic sulfide, and this upon mineral acid addition like HCl or something, you will get H2S, and then from the smell itself you can find out. In this case, if you add mineral acid, nothing will happen, no foul smell will come, whereas in this case and this case it will come. You understand that. Let us look at more closely such proteins, rubridoxin minus 60, ferridoxins some minus 400, ferridoxin 2 a different type, iron 2 Fe2S2 minus 430. There is something called high potential iron sulfur protein or iron protein, high potential iron sulfur protein or high protein. This is called the high PIP. So, high potential iron protein or iron sulfur protein. So, this has got high positive potential plus 360, whereas these are having minus values minus 400, minus 430, whereas plus 360. And flavodoxin is a flavin, not a iron sulfur protein, minus 420. So, here itself you can see the iron sulfur proteins can show as positive as plus 360, as negative as minus 430. The difference is 800 millivolts, as you can see that, a large amount of millivolt kind of thing. So, the iron sulfur proteins are very nice to study, and in fact, you can take an iron sulfur protein and do like to find out whether it is a 2 iron 2 sulfur protein or 4 iron 4 sulfur protein. How do we find out? Do a core extrusion. So, how will you do? Because all of these are associated with the thiol. So, use excess thiol. You take the protein and add excess thiol from exterior outside, and it will take the core out and the protein becomes the apoprotein. And you can check that absorption spectrum, and you can compare with the standard one, and you can identify by using the absorption spectrum, you can identify whether it is a protein has got iron with 4 thiolates a 2 iron 2 sulphur protein, a 4 iron 4 sulphur protein, or whether it is a rubidoxin, whether it is a ferridoxin of 2 irons and type, is a ferridoxin of 4 iron type. You can absolutely find out from the absorption spectrum of these enzymes. How? By adding excess thiol to the protein and extracting the core and looking at the absorption spectrum and comparing with the standard one. Similarly, you can also look at their EPR spectra. See, the EPR spectra of the iron 1 iron protein, see, looks very nicely around between 4 to 5 is the G value. Now, if you look at the 2 iron 2 sulphur protein, you can see these are the things, and if you go to 4 iron 4 sulphur, this one, this one, this one, and these three are very similar, and intermediate to this 2 iron and 4 iron is the iron high pip. So, that means if you look at the absorption spectrum, if you look at the EPR, you can identify whether it is a 1 iron system or 2 iron 2 sulphur system or 4 iron 4 sulphur system or 4 iron 4 sulphur with high pip system. All these can be very well identified from the absorption spectra, from the EPR spectra. It is very interesting, very simple proteins. So, you can just do the core extrusion and then compare with this. So, if you have iron sulphur proteins, first thing is you can do a test of the mineral acid and you can find out whether there is an inorganic sulfide is there or not. So, if it is there, now the next question is that whether it has any iron 2 or iron 4 sulfur. So, how will you do that? Take let us say a protein mix. So, then say iron sulfur protein, and you want to identify which one is this. So, first is HCl, and then the H2S H2S no. So, this means this is iron sulfur 1 iron protein, and if it is S, it could be 2 iron 2 sulfur or 4 iron 4 sulfur. So, you can measure absorption, you can measure EPR. From this you can differentiate 2 iron 2 sulfur versus 4 iron 4 sulfur versus 4 iron 4 sulfur, which is a high PIP. So, all these can be identified very nicely, very well in this kind of things. Okay, so having seen this, we talked about the iron sulfur proteins which are having a negative redox potential, high P proteins having a positive 400 360. Why are these having the positive redox potential? See the example over here, this iron sulfur protein and the protein is surrounding. They are buried. Number 1, the high pip iron proteins are buried, the iron sulfur cluster is buried inside, and second thing is these things are stabilized by the NHS hydrogen bonds. You see NHS hydrogen bond, NHS hydrogen bond. There are so many. So, these the sulfurs, the thiolate sulfurs as well as the inorganic sulfides, they are stabilized by the hydrogen bonding. They are stabilized by the hydrogen bonding. So, they are interior. So, the two reasons, one is they are inside the protein, they are stabilized by a large number of hydrogen bonds with the cysteine sulfur with the inorganic sulfur. Therefore, their redox potentials are very different. Hence, boon in disguise, iron sulfur proteins will go from -400 to +400, even more range of the redox potentials. Now, let us look at the redox characteristics. The redox characteristics. So, I told you 1 iron protein. 1 iron means there is only 1 iron center. So, that iron center iron can undergo what? Iron 3, iron 2. That is all. So, you take iron 2 into 4 thiolates, then you have a 2 minus, because 4 minus 2 plus 2 minus, and then 1 minus, that means iron is 3. So, it can only have one type of one possible redox. reduced protein will go to oxidized, oxidized protein will go to reduced, because one iron, therefore 1. Now come to the 2 ions. So when you have 2 ions, both the ions can be in 2 oxidation state, or both the ion can be in 3 oxidation state, or both one ion can be in 2, other ion can be in 3. Those are the 3 possibilities, 2 iron, 2 sulfur. Okay. So you take thiolate as 1 minus, sulphide as 2 minus, iron accordingly you can calculate 4 minus and 4 minus 8 minus, out of that 4 minus is there, so 4 plus, the 2 ions, so 2 plus. So the 2 ions 2 plus, and this is now 3 minus, means 1 iron 2, 1 iron 3, and this is 2 minus, which is both the iron 3. So both the iron 2, 1 iron 2, 1 iron 3, and both the iron 3s. So this is called super reduced, this is called reduced, this is called oxidized. The protein can never undergo between the reduced to the super reduced. It can only undergo between reduced and oxidized in case of Fe2S2. So 3 possibilities as far as the complexes are concerned, but the enzyme show only these 2. Enzyme shows only these 2. That is 1 iron 2, 1 iron 3, or both iron 3s, but it will never show both iron 2. So ferredoxins will not show, 2 iron ferredoxins will never show super reduced or both the irons 2. Similarly, when you have 4 ions, there are so many possibilities, all 4 in 2 plus, all 4 in 3 plus, or 2 of them 3 plus, 1 2 plus, etc., etc., etc. All these possibilities are there, of which the most favored are shown over there, and this is 4 iron 2s, 3 iron 2s and 1 iron 3, 2 iron 2s and 2 iron 3s, 1 iron 2 and 3 iron 3s. Of course, you can have all 4 iron 3s, but never found even in small complexes. But in small complexes, these 4 are being found. But in protein, if you see in the regular these things, ferredoxins, you can find between iron reduced, which is this one, to oxidized, which is this one, and superoxidized. In regular ferredoxins, regular 4 and 4 sulfur ferredoxins, let us see 2 iron 2 sulfur ferredoxin. So you have FD oxidized to FD oxidized to reduced to oxidized. So this is 1 iron 2 plus 1 iron 3, and this is 1 iron 3 plus iron 3 plus. Both iron 3s, 1 iron 2, 1 iron 3. This is only possible in enzyme. And now, if you take 4 iron 4 sulfur case, you have so many possibilities are there, of which the 4 iron 4 sulfur enzymes. Okay, 4 iron 2s, 3 iron 2s plus iron 3, 2 iron 2s plus 2 iron 3s, or 1 iron 2 plus 3 iron 3s, and 4 iron 3 plus. This is never found, only these 1, 2, 3, 4, 5 is never found even in complexes. Only these 4 are found in the complexes, and of which the FD reduced, FD oxidized, FD super reduced are found in the proteins, for the normal proteins. So this is what 3 iron 2 plus iron 3, 2 iron 2 plus 2 iron 3 plus, and 1 iron 2 plus 3 iron 3 plus. So this is in normal ferredoxins. and in high pip, and this is the other way. So, it is the super reduced to oxidized. So, high pip reduced to high pip oxidized. Okay. So, that is 2 iron 2 plus 2 iron 3 plus going to 1 iron 2 plus 1 iron 3 iron 3 plus. So, only these are the two forms are possible in these systems. Okay. So, if we try to look at these, try to understand what happens at these, from small molecules it has been found the 3 iron 2 iron 3, 2 iron 2 2 iron 3, 1 iron 2 1 iron 3. When you look at the crystal structures from small molecule, this iron-sulfur distance versus thiolate distance, you go to this 2.233 becomes 2.267 becomes 2.354. Look at this distance also similar way increases. You look at this 2.208, 2.263, 2.295. So, what is happening? As you keep oxidizing one ion from here to here, one more ion from here to here, these are basically expanding. So, therefore, you have an expansion when it is oxidized and it will contract when it is reduced, oxidized, reduced. So, that will bring accordingly conformational changes in the protein that is bound, and that is what is involved in the electron transfer process. So, in the electron transfer process of these iron-sulfur proteins, there is a reduction, oxidation takes place. During that period when it oxidizes, it will expand, it will reduce, it will contract. So, expansion and contraction of these cores will basically involve in the protein conformational changes, and such protein conformational changes are basically responsible for the protein electron transfer. So, with this I close the electron transfer part, and then I will go into the enzymes in the next class. So, I have explained the basic principles of electron transfer and some examples of the heme non-heme ion center. Thank you very much.